I had mentioned that there would be a lunch get-together for the CS students planning for the fall semester, and that we just could not do that just because there was a little bit of a chaos. We have an administrative assistant, and she was unable to. She wasn't here, so we just couldn't coordinate it. It's going to be tomorrow, so tomorrow at lunch. I'm gonna not really strongly advocate for you to be there. The reason is this is more than what you would find on Homer Connect about what's going to be available, but we are going to be projecting some things into the future. And if your graduation is not like in December, these things will actually be hopefully meaningful to you. And you'll hear me talking about our new minor on systems, which significantly overlaps with cybersecurity. And it's not just an intention to teach courses, but we actually have a new lab being built within the next month. We have the formation of an internship on campus, and there's a whole bunch of things that I want to actually outline. So I definitely hope to see you there tomorrow. Is there anyone who, despite wanting to be there tomorrow, won't be able to make it for a reason? So what are the reasons?
I have my scholarship meeting. That is a requirement.
That's a requirement on Piper? You have to work? You also have work. Anyone else? Yeah.
I have class.
You have class. At that hour?
Yes.
Really? I thought that actually registrar doesn't allow those, like Tuesday and Thursday noon hour.
It's
Wow. Well, okay. All right, so for the 4 individuals, could you actually send me an email as to when we should get together so I could repeat this for you? Okay? So I'm hoping to do that maybe, like if you could give me as generously as possible, like your free hours Thursday and Friday, then I'll try to come up with something for you so that you don't. Again, for those of you who just came here, what I said was the advising meeting that we were supposed to have yesterday over pizza. We were unable to do it for coordination reasons. We're going to be doing it tomorrow. It's going to be in this room from 12 to 1, and we will be outlining some of our new programs as well as some like career-oriented things that you could get out of this program. Okay, so let's see. Let's see. Dalton, remind me what we were doing last time we were here.
You were talking about like the
Yeah, you said enough. Like you were just trying to remember the name. Like you were here and you're.
Yeah.
It's got 3 words: finite,
Yeah.
state. What's the last one? Finite state machines. Yeah. Some people will actually call it a finite state automata, which is like the original name, but it sounds a little pretentious, so we call them machines now. So we are still dealing with finite state machines. Okay, and then the acronym is always like FSM. I suspect you would have guessed that. So there's a formal way to define finite state machines. It actually was, let me give you another pretentious word, it was a 5-tuple. So a finite state machine, FSM, finite state machine M, is equal to a number of variables. Whether you remember or you look up your notes, does anyone want to, could anyone help me here? How do you define a finite state machine? Yeah.
I think the first is a set of all states.
We called it Q. Was it Q? Okay. So we're going to define it one more time. So we have a set of states, Q. Okay. What else?
Then we have an initial state.
Which was S, I think. Yeah. Parker?
There was sigma. I was
Actually, so what I'm going to do is I'm going to actually write them in the order that I hear them. We'll put them in the standard order just because, just to be standard. It's not actually nothing, right? You said sigma, right? Sigma was, we'll ask what they mean. Anything else? Yeah.
It was delta.
There was delta. Yeah. Looks like an F. Yeah. And then finally, yeah.
An F, so
Was it a lowercase or uppercase?
lowercase.
we had lowercase. I'll actually write it lowercase, and then we can collectively decide to make it uppercase for a reason. I'll mention it. So here's this. Okay. Now, was this the order that we had them in? What was the difference?
You swapped sigma and S.
These two were swapped?
Yeah.
Okay, we'll just do that. So I'm gonna write it both. For note-taking convenience, I'll keep it there. So we initially defined it as okay. Now I'm interested. Yeah.
We didn't have it as.
Oh, you mean this?
We didn't have it as.
I thought we did. It's the initial. It's the starting state.
Was it
It was initially Q0.
Oh, it was Q0. Okay. I'll call it Q actually because it is kind of like an element from this. So I'm just going to call it Q. I won't put the 0 because it's the lowercase letter. It's going to be like an element from this Q. So I'm interested in hopefully from like different people. What do these individually mean? Jaden, you had your hand up like a minute ago. I can get to. Do you want to take this?
Sure. The first Q is the set of all of the states.
Set of states. Cool. Anything else you want to offer?
Yeah, the sigma is the alphabet or ASCII.
Yeah, it's the alphabet. Okay. Anyone else?
And Q is the starting state.
So starting state. Okay, delta and F. Yeah.
Delta is the functions that change states.
Okay. We'll call this actually the transition function, but it's what you said. Transition function, and then delta. Oh, that's actually the one. And F.
The final state or final states.
Final states, yeah. Subset. I'm gonna write it as subset of final states. Yeah. So now, what we're gonna do is, and once again, people are taking photos, and I'll actually just step away from it so they can have a clear shot of it. But I also want to repeat my point that when you are writing this in your own words, like doing the more laborious thing, you are internalizing the material as opposed to simply preserving information. And I would just advocate for you to do that, but I'm not going to interfere with how you actually take notes. So, do I have this clear? Like, did I make a mistake? It seems to be fine. I don't think that I did. I'm just confirming that it seems fine. Okay. So the reason I wanted to actually make one modification is that I'm going to say, let's not call this little f. Let's call this big F, for the reason that it is a subset of Q, but it is still a subset, right? And we tend to use lowercase letters to represent elements and uppercase letters to represent sets. So this actually would not be incorrect at all. I'm just making things easier for my human brain to remember, so that when I look at Q, I know it's an element, because it's a lowercase. When I look at uppercase Q and uppercase F, I know that those are sets of vertices, or of states, yeah. So now, this is gonna be interesting. So raise your hand if you were not here last class. There's 2, 3, 4 people not here, 5 people not here. Now, what I'm really interested in saying is there anyone who was here last time who can, under a minute, give the gist of what this thing is supposed to be? Because if you actually missed that class, you just showed up and what used to be a math class became a Greek class, like there's the Greek letters here. So I'm wondering, and again, this is our practice to improve how articulate we are. Can someone give me the gist of what this thing was about?
It's an algorithm designed to take a specific order string
Nice.
and result in a final state from an original state.
Mm-hmm. Everything that you said is great so far. There's more to be said, but everything you said was correct so far. Do you want to add more, or should I go with someone else?
And if the wrong input is entered, then it will reset to the to a prior state.
Yeah, so the machines we did on Monday did that. I don't think that's part of the definition, but they kind of like did that, yeah. Is there anyone who wants to offer anything else? So again, the people who raise your hand, Gianna, you raised your hand, right? So we heard Parker give us a few of the qualities, characteristics of these things, but so can someone else maybe do a version 2 of this? Like, what are finite state machines and why are we interested in them? When I say, can anyone explain this well under a minute, that's actually a tall order, but we have to keep doing this, like, right? Like, there's gonna be 4 years of tall orders for you in these moments, so that's why we improve, right? So this, yeah.
I'm thinking sort of an implementation of it would be, we talked in class, like a vending machine, like
Mhm.
something where you need you need to know a specific way to deal with how the user interacts with the machine, but
Mhm.
maybe you don't need something as complex, like, you don't need like a whole operating system on it.
That's the abstraction part, like finite state machines, it's not a mechanical machine, it's not an electronic machine, it's an abstract machine. Does away with all the details. I have something to say, but I don't want to I want to defer to you. Does anyone else wants to add another version of this? So during EdTech Day, we had a few FBI agents stop by, and they were looking at our lab where we will be doing some cybersecurity experiments. We actually want to get their take on it. They were really impressed. And the students who did a phenomenal job, to the point that the FBI agents actually were willing to kind of like offer them internships, especially if things work out. Despite that good of a presentation, what I noticed our students do was the following. They said, so in this lab, we have these machines interconnected this way, those machines. What I thought would be good to give a big picture view. So for instance, we have this space that is disconnected from the internet, and we are creating our own disconnected, brand new mini internet for us to conduct some experiments. Like, the value of that sentence is very significant because it contextualizes the work, right? So I'm gonna apply that principle here. The purpose of this is the following, that you're ultimately coming up with a black box, which is the finite state machine M. Into it goes strings of input, and out comes true or false. This is basically what a finite state machine does. It's this abstract machinery that you submit a string of symbols, and then it says either true or false, or accepted or rejected, some positive, some negative. And what that means is, going with the example of, like, you mentioned strings. So I could say, I'm gonna design a finite state machine that will say yes to every string that ends with A and B. Like the very last letter is B, the second to last is A, the stuff that comes before it doesn't matter. So you're saying that I'm going to design that machinery so that all the infinite number of strings I could put into this thing's going to give me a true if and only if the last letter is B and the one before that is A. Okay? So this is the kind of thing we're doing, and the reason we do this is because this actually becomes part of translation. When you write Python code and it's executing on the machine, there's a translation involved. And one of the things that the machine does to be able to do that magic is actually use finite state machines to check the grammar of what you wrote. So these are phenomenal objects. So here, going back to this sigma is going to be the accepted set of characters that you can assume to be part of the string. So if I'm actually taking series of, like, if I'm taking a binary number, ones and zeros, the sigma will be 1/0, and that's it. But if I'm taking, like, English sentences, it's going to be lowercase letters, uppercase letters, punctuation, and so on. So I feel like we're okay with this. Is that okay? Ari. Thanks. So what about Q? What was Q? It's sort of obvious, but I still want to hear it. Yeah.
A set of all possible states the machine can be in.
Yeah, the machine can actually be in an initial state. It's just ready for, like, get first input, and then it could be, yeah. So this is basically all the different states that the machines can occupy. So it's going to be a finite state. This one was Q. Ben?
Starting state.
Yeah, you must start there. Yeah. And F is also you.
The final state that the final states that the machine can read.
Yeah, so the moral of the story is you're in the initial state. Based on the characters that you're receiving, you do transitions from state to state. If you wind up at one of those so-called final states, when the input is exhausted, that means that you've actually accepted the string, you've said yes, you said true, and so on. But if it's not one of those, then the input was flawed. Okay, there we go. And then this actually is the transition function. And we did say this. We said that delta is a function that goes from the Cartesian product of the states and the alphabet to this. Can anyone, again, we are learning a language. This is remarkably dense. I would like someone to, in the best, most articulate way, turn this into an understandable sentence in English. I'm gonna go with Chaz if no one else volunteers in 5 seconds. Go for it.
Okay. I guess the input, or I guess what you're starting with is like, okay. I'm trying to use like not the terms we're using in this course.
It's hard, man. That's why we keep doing this over and over.
Yeah. So all of the possibilities of the characters and like when the characters can appear, so like the sets or the states, I mean, all of those will result in like a state.
That's not, yeah, it's difficult. Is there anyone, Chaz, you want to try?
You put in a set of all possible set of states, and the inputs are all possible set of states, and all in the set of all characters that we use in the string, you get out the state.
These are correct, by the way. Your roommates wouldn't understand you unless they're computer scientists, right? Yeah.
I guess I'm gonna try.
Sure.
But every combination of letters that can exist will result in at least one combination of letters.
Okay, okay. So I guess
Or
I,
the opposite, I mean,
now
it's
you
not
could say,
necessarily
you could say that
letters.
this is cheating, but what I'm gonna say is I could actually draw something and I would say, like, you see these arrows? You follow these arrows based on 2 things. Where you were and what was the next character that you saw. So you combine them. If I'm over here and I get this letter, I go this way. If I'm here but I get a different character, I go this way. So you have to combine the next thing that you read with where you were before you can figure out where you're gonna go. So you need those 2 things. Can anyone actually whip out real fast finite state machines that will tell me every even number? This is all of a sudden sounds like, whoa, what happened here? But it's actually not that hard. I want you to give me a finite state machine that recognizes positive even integers in binary. Positive even integers in binary. Not JD. Yeah.
What I'd say, so you start with, let's say, I guess it just need 2 states.
Okay.
So. let's
And I'll
start
call
with-
this A and B.
Yeah. So say A is the starting state. and,
Okay.
I guess that'll be the true or false. So then what it would be is, so we're just going like number by number.
I can put in any binary string,
Okay.
and it should tell me this is an even number by the accepting state, the final state that I end up.
So it'll be, there'll be an arrow pointing to B
From A, right?
Yeah.
Okay.
if the final bit is a 0.
So a 0 takes you here.
Yes.
Okay. And then? So what happens if I'm here and I get an A?
You'll loop back to itself.
And then
so,
here?
So are we looking through the entire string then?
Yes.
Or, oh,
So what is the definition of being an even integer in binary? Yeah.
You need an arrow for it's going again that goes back to.
Yeah, this is incomplete. I'm just asking you a question that actually really makes everyone get this. Like, what is the definition of an even number in binary? Yeah.
It's any number that ends in 0, because the last digit will always be 1, which is what causes an odd number to become odd. Otherwise, all of them are even numbers.
Exactly. So look, decimal 0 is 0, decimal 1 is 1 in binary, 2 is 1, 0, 3 is 1, 1, 4 is 1, 0, 0, 5 is 1, 0, 1, 6 is 1, 1, 0, and so on. Yeah.
So then to continue on this, then I guess since only that first bit matters, then there'll be two arrows pointing back into B, like an arrow for 0 and for 1, because
So I think that you specified like what happens when I'm at A in the two bits that I can counter. You haven't said anything about B, like what happens when I get a 0 versus a 1 in B?
it doesn't matter, so it'll.
But that means that that's not a function anymore. Because you're telling me like your delta doesn't know what to do for a particular element from the domain.
What I'm saying is, you'll have an arrow looping back into B
Under what circumstance?
for either of them. So you could have.
He has had to stand up for so long. Actually, I just want to go, yeah.
Would it be a move back if it was 0 and then could go back to A if it was 1?
Exactly wrong. So fix it.
Would it be a move back if it's 1, goes back to A if it's 0?
Because remember that if you end up with a 0, it's an even number. So this is representing actually the last thing you have seen being a 0. So if you actually see a 1, you say, oh, duh, I go back to square 1, or in this case, circle 1. And then, so this actually is, and I want to see like if you're convinced of this.
Yeah, I said that.
Oh, is this what you said?
Yeah.
Did I hear that wrong?
Yeah, that's what
All right, fuck, I'm sorry. I make mistakes too. But there's one thing missing here though. Yeah.
You need to make B the final state.
Yeah.
You need like a third set at the beginning because if the number is 0.
Robert, like I make mistakes, guys. But if okay, now that you're laughing at me, I'm gonna land on you like a sumo wrestler the next time you make a mistake. I'm just kidding. I'm totally kidding. Yeah, go ahead.
As it's written right now, a final state could be 0, which isn't an even number. So you just need a state before A.
Yeah, so that actually is weird because it looks like if we haven't seen anything that actually, so this really is not doing this part right here. Does anyone know the fix to this? I don't. And it's possible, but I don't know, like what would you do?
I would, like, before the grounded state, just make another set, and if it's 1, go to A, and if it's 0, go back to itself. Because 0 could technically be like 0, 0, 0, so just loop back to itself 3 times.
Okay, so you 3 states?
Yeah, it would be before A though. Oh, I see your technical.
Yeah, like I'm gonna make A, B, and C, and this is the accepting state, and I think this is gonna be accepting also, right?
No, because that will only ever be 0. Because if it moves to 1, then it'll never go back to A.
Okay, so we might be thinking different things, and again, I could be wrong, by the way. Don't laugh too hard. Yeah.
So I guess I'm trying to understand how this. So you have to go back from you have to start from the starting position every time you do a new binary state, right?
It's based on the arrows. I don't have to go to the beginning.
Okay.
In fact,
So-
it might be good for us to reverse engineer ABBA. That was one of the examples. That doesn't go all the way to the beginning. But let me do this. Let me do this before. Yeah.
Sorry, I'm just trying to understand. So in that case, why is there, since you only need to look at that first bit, and you know you get to B, why is there an arrow pointing back to A?
Let me ask you, do me a favor. I'm gonna put that as the inputs. So 1, 1 comes in. So I'm here. What happens when I have a 1?
It loops back on itself.
Another 1?
Yep.
And I'm done. That's not a final state. This is rejected. It's not an even number. It's an odd number. Let's try this one. So I get a 1. I stay here. 0 takes me here. 0 takes me here. You were thinking of it the other way, right?
Yeah, I was just reading from right to left. for some reason.
That's why I wanted to shift to the example, because I knew you got it. It was a direction thing. Yeah.
Why does 0 not work?
Here?
You just get 0, you have 1 to 3.
No. It's actually, oh, I see what you mean. It does work, that's right. I am so good that even when I think I'm making a mistake, I'm right. No, I actually was thinking that if it's non-existent, like the input was 0 length, this would actually give you a rejection. But I think that's an interpretation thing. You could say that no input actually is not a rejection, it's an acceptance. So you could say that's when you have to have a state that initially is initially accepting, and a 1 would take you to a non-accepting state, and a 0 would take you to an accepting state, and then you would repeat this machine that we had this one here. Just so that you would say a 0 length input is also accepted. Yeah. Very good. So can you actually do this on a piece of paper on the whiteboard? I prefer the whiteboard. Can you come up with a finite state machine that recognizes the band ABBA, and the input is the alphabet is like 26 letters, everything lowercase. See if you can come up with it. And we did this, but I would just want to see you do it one more time. Did you understand?
Just the ABV. Yeah, they're just trying to find.
So, actually, let me invite the others also. Ari? Amir? Amir? Do you want to keep working with them, or you want to do like a little mini lecture here?
With you?
Yeah.
Okay,
Yeah. And then who is also?
Oh, yeah, I guess you can.
Yeah, so we actually ended up doing this additional topic this semester because it's a wonderful application of functions and relations. Finite state machines is really an important thing in computer science. We just don't see them because it's not flashy, but it's actually a very foundational thing. So ultimately, you're coming up with this abstract machine, which means it doesn't really physically exist, but it's kind of like a calculation, like a black box, that says, give me an input, and then I will tell you if that input that you gave me complies with the rules that you have told me for acceptability. So for instance, I could say that even numbers are acceptable, odd numbers are not acceptable, like that kind of thing. Or I could say that any input that has an AB at the very end is acceptable, and anything other than that is unacceptable. Okay.
Is that your
I guess if you
He's like
I thought
he thinks he's like a professor.
Yeah. I thought it was like some prodigy student kid, like just in this college level class.
You can't tie his shoes. Literally, not figuratively. Anyway, so this is what we are doing. So what we are saying is that it's going to be things like this. Now these circles represent state. It would mean that like the machine is currently thinking that it's like this is where it is, but it could be another place. So for instance, you could be in a sleep state, you could be awake, or you could be hungry, or you could be angry. Like, you know, you can find the states that you individually could be, and this is the machine version of that. So we're saying that given this set of states, these transitions indicate how it consumes the inputs character by character, eventually making a decision whether the input was good or not. So you have a bunch of states. One of them is designated as the start state. And then after that, so this one was, let's say that the input was 1, 0, 0. This is the string that I give it. So it says it's going to consume it this way. It says I must start here. And then if I'm here and I get a 1, the other possibility is 0. If I get a 1, I stay. If I get a 0, which was what happens next, I transition into this. So at this point, if the string ended, it actually ends with a 0. That's actually the definition of even numbers in binary. This has one more 0, and when it sees another 0, it keeps staying where it was.
And is it storing the zeros in that?
It's simply eating them up and then telling you where it was when the whole thing was eaten. And the final state indicates whether the input was good or not. And so the final states that indicate good input are double circled.
So is
That's right. And in fact, that's what I was doing. Like, let's do this one, 1, 0, 1. So that's
essentially what this is doing is finding whether it's an even number.
Yeah, exactly. Yeah, so let's do 1, 1. So tell me, I get a 1.
I'm saying it's saying an A.
Then I get a 0.
It's gonna go to B.
And then I get a 1.
It's gonna go back to
And no good.
and that's not good.
I mean, no good is not really no good. It's just a not
Like
number.
what, returning like false or something? Like,
Yeah, exactly. But the thing is, like, so in fact, one of the things I'm going to ask people to do is the following. Tell me in Python, how do you assign a variable to a number? Like, give me any example.
A equals 3.
A equals, so this is a variable.
Yeah.
What are the rules for variables? Like what are the rules that govern what makes it a legitimate variable?
I feel like it's immutable unless you.
But like, so for instance, like, is there a limit to the
Oh yeah, I think so.
We don't run into it. There might be one, but as far as what we have seen, it could be anything. Like it could be 10,000.
Yeah, if it's like a string.
Yeah. But can I do this thing? Can I say 1A is equal to It doesn't accept this. It actually says that variables must start with a letter. But then after that, like this is your variable is constant. So how does the system decide if a variable name is legitimate or not? They define a finite state machine to eat up the variable name, and if you finish in one nice acceptance state, it says, oh yeah, this is a legitimate variable.
So what states does that look like? Is it like looking whether it's a number or a letter?
We're going to do that actually as an exercise. Yeah. But so you just have to come up with something similar to it, and you have the luxury to do this. So you can say, if it's 0 through 9, like a digit, keep staying where you are. Like you can condense these
Oh,
things.
right.
So you just come up with you'll just come up with a state machine that, to the best of your ability, represents what's a legitimate variable.
So A here could represent the entire alphabet.
Yes. Well, it's not A actually, it's the transition. So the entire alphabet, like you could say, so I can do this. Tell me what this means.
Then it would be in the final state.
It goes back.
Oh, A through Z.
Lowercase.
Oh.
So if it has an A, then it has to go B, B, A. Like B, B, like A, B,
What does this mean?
Yeah, exactly. So that B is A, B.
I like kind of
It's just saying like what letter A.
Yes. So there are 26 things here. Like any of those will stay
Oh, so
Something with one letter capital. Oh, it's just telling you if it ends with capital.
This is a machine that detects any variable name that ends with a capital letter.
that ends with a capital letter.
Yeah, because if it's a lowercase letter, I keep eating it up, like the next character of the variable name, next character of the view. But if I see the uppercase one, at that point I transition to this final state, if that's the end of the state. But after that, if I see some number of uppercase letters, I don't go anywhere from it. But then if I see a lowercase letter, I come back to this.
And then when you come back to here, are you staying in the lowercase? Like, are you still looking through? So if it's like lowercase a, capital A. Oh, right.
So that takes me here.
Yeah,
This takes me here.
Yep.
Let's look at this one. Is that the first one?
You're right.
It doesn't end with a capital.
But if it's like lowercase a, capital B,
And do we have to memorize exactly what each one of those are? Or
I'm going to ask people.
Yeah.
Things like check this out. Like this thing is it's saying that this is the transition function. And I'm being consistent with the CS literature. That's why I'm taking out Greek letter. I'm going to have to wait for like this. Like the transition function in this thing is called the delta function. Given the scenarios, I guess a couple of particular symbol that would be there. So in other words, like I'm here and I know lowercase.
sorry, so the starting point?
It's like if you are in any, so like if I look at this one, let's do a Cartesian product. So this is my A state, this is my B state, and this is an input of 0. Input of 1.
A.
That's what I was wondering, but.
and Q is representing all the different.
This is Q.
Once you do this.
Oh, that's
This is Q.
What does that
and look at this one. Yeah. So it's saying that if you are at A,
like how do you get back to
C,
C?
you transition into a particular state. But if you're in A, you get a 1, you could actually make a transition to a different state.
Yeah.
So that's why this notation that we saw in chapter 4, I think it was the functions, the Cartesian product of two domains, two domains, that could be the domain of a new function. Yeah. And the thing is, like, if you make this innovation, you get a different kind of new which we are studying tomorrow.
It doesn't, we're like.
Yeah, that's the initial state. That's the initial state. That's basically me doing that. Like, it always does matter.
Once you see that there's an
People like calm down.
Okay, yeah.
This is good, right?
Yeah, that's not that.
Hey guys, everyone, may I please? So may I please actually hear what you have? I wanna give you like one more thing after this, and then one more thing with a surprise in it, and I want to be able to do all of them. And by virtue of being here, you get the quiz credit for today. Did we ever do the zebra thing or the?
I don't think you did.
Okay, so
I never saw it.
so we'll do two of them, and this one I actually have. So what time is it? 36. Okay, so we'll end the class like 45, and I'll design 2 quizzes, each one with a bogus question. Just by being here, you can do that. Which means that. Yeah. So what do you guys have? The one up right there. Now, as you're explaining it, everyone should be checking in against it. We're interested in how yours might be different. So go ahead.
We basically have 5 states that
Okay.
that's actually not going to explain. So you can be in the starting state where you
Okay.
A or B. B, you back into yourself.
Okay.
A, you move forward.
Okay.
A, you look past yourself.
I love that.
B, or like, and then 3, it's A, back. And you get the 4, and it's B, all the way back to the beginning. So there's
This thing is key. Because you actually, when you see this A, it actually prevents you from going to the final state, but it still accounts for the very first A.
Yes.
That's excellent, yeah. And then the final state is the accepting one.
And then if there's more, it just keeps moving back onto the final state because you already have it. Yeah.
Excellent, excellent. Okay, so is there anyone who's exactly the same? Almost? So yours is exactly the same. So, okay, I'm not gonna talk to you because we heard that. You have the exactly the same?
No.
No, I think ours is a little different. We don't move the second one to itself.
So you had B go back, and A takes you to the next one.
You had A go back to the beginning.
Yeah, if we get an A here, it goes back. If we get a B, it goes to C.
I think that when you get an A here, it should go back to itself because that A, that second A that prevented you from making progress could actually be the beginning of the actual ABBA. So it basically mimics like that very first one. So from B,
It goes back.
yeah.
It goes back to itself.
It goes back to itself, yeah. It's accounting for the fact that it could be the next A you were looking for. Yes.
I was gonna say I made that same mistake. So,
It's the same as yours?
yeah.
Oh, you made the
that
mistake.
same mistake.
Oh, yeah. So you guys had the same thing?
Yeah, we just added, we thought it said like the entire alphabet, so we included that as well. So we have A, B, and we define C, which is not A or B. So,
You define, the same, yes.
Yes.
Okay.
So for like example, the starting state, if it's A, you move on. If it's not A, you stay at the same. Like if you go like to the end, if you have A, B, B already, if it's A, you move on and then loop. But if it's not A, you go back.
I want to make a note of this. This just means that whatever you see next doesn't matter, you stay there. And instead of enumerating every possibility, you just put the name of the alphabet there. Yeah. Is there anyone who wants a clarification on this? Like, are we ready to move on to the next one? And we should never move on unless someone doesn't get it. Like, we're all good, right? Any questions? Okay, next one, and I'll give you like 5 minutes for this one. It's actually easier than ABBA. Can you come up with a finite state machine that detects every string that has, it's gonna be basically strings over A and B. So you have nothing but A's and B's. It's gonna detect strings where it has, the number of A's is a multiple of 3. So if it has like, you have 3 A's in it, it's gonna say yes. If it has 6, yes. But if you have 5 A's, it's gonna say no. So we're looking for a machine that detects strings over A and B such that the number of A's is a multiple of 3. 5 minutes.
Does 0 count as more than 3?
Wait, can you explain, like, say that quickly?
Like in the word hello, there are 2 L's.
Yeah.
So if I was designing a finite state machine that's looking for strings with 2 L's, hello would be acceptable. But if I say with 1 L, HELO, it would say no.
No.
Because the number of L's is not a multiple of 2. So we're looking for a machine looking for the number of A's being a multiple of 3.
Multiple of 3. Okay, so we should set like an example of like A, B,
So stuff.
A.
This is the theory that is no longer covered.
Well, we're saying.
And if you were to take like programming languages, depending on who teaches it, this is like
This
the
is just an
first
example.
That's cool.
Yeah.
I got approved for networks at Canterbury.
Nice, very nice. Yeah. Do you know what that's
I don't know. I didn't look too much other than just schedule. Make sure they're timing the classes line up.
That's great.
I can look now. I have it still resolved.
Yeah, I'm kind of, if it's the same thing, then you're taking the same class.
Yeah, and then I switched, so they approved me for a couple of my classes, but I switched. Then like a month after I sent my application, I realized that there's a couple of classes that I just didn't really want to take. So I also signed up for
The total number of A's is a multiple of 3.
Total number of A's is a multiple of 3.
I also signed up for database. That's getting approved. It hasn't been approved yet. The classes line up, so I'm sure that I'll get approved.
It was meant to be.
Yeah, it'll be good. It'll work out. And then there's also this cool history class on Alan Turing that I'm gonna take.
Which one?
It's just Alan Turing. It's like a history class.
Alan Turing?
Yeah. Just like about all the stuff that he's done and falsely. All that. Yeah. It's good. I think it'd be a really cool class.
That guy was amazing. The only negative I know about him is didn't care for most of the But like that's such a detail. I mean, I actually felt like racist things about him.
Oh yeah, you're right.
Yeah, I mean, it's there's a lot of interesting stuff that he discovered and thought about it.
You know, he actually was curious about why when you have like a cat, like a tiger cat, the stripes on one is the same, and then don't know what they're supposed to be doing based on how the hell.
How does it still do that?
And the cellular automaton is what he worked on. Nobody talks about this. They always talk about Turing machine.
Yeah. Yeah, well, my cover in my class is a whole semester,
Because
so.
like this regular A,
Yeah, I think we need more.
more states. Oh right, or for like single A, single B. I guess it's just the. I mean, you're right. I don't know. We're looking for this. And there's a clear difference between these two A's. I feel like that's the different type of states. So you can have one state that's regular A, one state that's triple A, one state that's regular B.
Yeah, like that. Like
State that's
it can be.
How many, how do you know how many circles? Whatever you want to do. How do you know where to start though? Like I don't know.
Because like this was like given like we just.
I got the idea and like how it's.
When it's something like this,
I think you can end in A or B. Just has that.
it's either a good or false. You can have
Also, interviews like that. I don't want to just know that you answered it correctly. How good is your justification?
I guarantee it.
Is there anyone who's done?
I bet my bottom's off.
All right, can I please have yours?
Yeah, so when you start at 1, if
Okay.
you get a B, it loops back to itself because it doesn't matter. If you get A, it goes to 2, A goes to 3, A goes to 4. Once you're at the final state, if you get A, it goes back to 2 because you need 2 more to get to the final state for a multiple of 3.
Very good. And then, so what happens if I get? Oh, okay, okay, yeah. I think that works.
Yeah, for every state, if it gets B, it just comes back to itself.
Very good. Is there anyone who had the same, you guys had the same thing?
We have pretty much the same thing. We, we start at state 0, so the state numbers kind of correlate to the problem itself. So, like, you start with 0 A's, add 1A, 2A, 3A, and then, yeah, it's kind of like modulo, like with the remainders. So, and 3 loops back to 1.
Very good.
But I think the overall topology is the same.
Yeah. Javier,
Yeah.
you guys have the same thing or a different one?
We're confused. Well,
Okay, so I was gonna say, we thought that it would go, like, this one right here would go back to the beginning because you need to have 3 A's, right? So if it goes back to itself, does it not only leave you with like 2 if you get A and A?
I think if you get, do you want to explain?
So basically, when you get the last time, you are able to loop back when you get another A dash, you go back to second position. Which would make that I mean, that position.
Well, can you actually do, so can you do this? Can you put like a string with some number of A's and then trace through it?
I would have it.
Oh, you already have it. Okay, so can you write a little bit bigger though? 'Cause
I have a question.
Yeah.
My question is like, so if I don't get my input that I want, do I just start all over with a new string?
You determine that actually. So when we were doing ABBA, I get an A and I say, ooh, this is good. I'm going, right? I get a B, this is still good. And the next thing that I want is an A, right? Is a B.
Yeah.
But I get an A. So that's actually kind of like a letdown. But the thing is, that A that was a letdown could be the beginning of another attempt to detect ABBA. So in that case, I don't send it all the way back to the beginning. I say this mistake at this state actually is also the same as the first step that I took in that direction. Yeah.
Does it replace just that like character in place of like what you have already written, or does it starts the whole thing?
It doesn't modify the input. It assumes that maybe this is it talking to us. I was confused about when this thing was supposed to start. It turns out the second A ends up being the first A of the word ABBA. So I should go back to a state that accounts for that having happened. So you're not really changing the input. You're just saying that it's just as I have to reinterpret what I saw. So in some cases you go all the way back to the beginning. In some cases you don't, because the thing that was the mistake at a particular moment could have been the beginning of the next attempt. So you go to the second state in that sense. And I'm happy to talk about this. By the way, this is phenomenal. Like most discrete math classes shy away from this. It's really important foundational CS. So I don't want anyone not to fully comprehend this. So alpha stars are more than like, we're happy to talk about this. So are we good with this one? Because I'm going to give you the last one. All right. So let's see, how much time do we have? So in 2 minutes, anyone who comes up with a finite state machine, that checks to see if parentheses are balanced will not only get an A from this class, but I'm going to give your diploma tomorrow, graduated from CS. Matching parentheses. Look at how they're going.
What happens if you start with an
It's incorrect.
Okay. So it was imbalanced even if it's the same number, if it starts with an ending?
Yeah, you just have to, yeah, exactly. Like having the same number of them is actually necessary, but not sufficient.
That makes sense.
Well, let's say that's
So what we need is if it has like 5 open parentheses, then we need 2, 5, and we might not
This include nesting? Yeah. This is almost it's nested. Okay, so that like basically this would be okay, but check this out. This
yeah,
would not be
then
okay.
this is a different question kind of.
Yeah, there's no not.
You can't, like, can this not be a finite state?
Well, it sort of is like that. It's sort of like 10 seconds and then like explain why. If you have 3 A's, right? If you multiply the amount of 3's, it would be 0. And that's the goal. So if you were to translate this into like some sort of code about the going back, also like if you have it, so if you want it.
Hey guys, so it is actually 50 past the hour, and I feel guilty about keeping. You didn't notice the time, so I wasn't going to say anything, but it's not right. This thing, all eyes on me. This thing cannot be done with a finite state machine. But does anyone know why?
We sort of went, if you start doing nesting of parentheses, like something blah 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 blah, parenthesis, blah blah, parenthesis. Once you have to deal with more, it's like you would need to include extra states, and you need to expand the machine to consider nesting, and you can't do that infinitely.
You can't do that infinitely. That's actually 100%. Is there someone who can actually give me an even more concise version of it? Parker.
It's not finite.
Exactly. It's called finite state machine for a reason. You commit to a certain specific number of states, but the number of opening parentheses can be one more than the number of states you have. These things are not good at counting. And so there's a limit to what a finite state machine can do. And when you realize it, you go to the next machine, which we won't talk about. I just want to tell it to you. Those are called push-down automaton, which is a finite state machine coupled with a stack. They become more powerful in terms of what they can recognize. And I'm going to leave that up to programming languages to cover. All right, so wait. I don't have my phone. Can someone take a photo of the whole class, please, and send it to me? Can one of can you go to the door and take a picture of the class? No, Rohan, let him. You're not tall enough to take the whole class. Come on. Rohan, can you check the other Rohan? Look, show it to me.
It looks good.
Show it to me.
It's good enough.
It's good. Okay. Can you send it to me? Yes. Like, is everyone in it? Go to that wall. See, you can take a photo of that right now and just send it to me. Like, I don't think they were included.
उसको पूछ के दे यार, पूछ के दे. अरे
All right, guys. Thank you so much. See ya.